Just talk more about sequences here. And let's do, yeah. So last time we talked about sequences for a bit, and although I might not have been as explicit as I could have been, when we were finding the limits of the sequences, we were determining whether or not those sequences converged. So for example, if someone gave us the sequence, say, I should write like, this is Co-17A in the PM or the afternoon, and today is 10:10. So for example, does the sequence, ah, my gosh, can I make an E? Maybe. Does the sequence A sub n equal to 5n plus 1 over 4n minus 2 converge? So I like to just ask, does it converge? And then the answer can be yes or no. You could also say, does it converge or diverge? And then you can say it blanks. It converges or diverges. So when we ask this question, what you should see when that is the question that comes up is, oh, does the limit as n goes to infinity exist as a real number or not? So the question that's really being asked here is, does the limit as n goes to infinity of our sequence exist? That means it would converge. Or not exist. That means it diverges. So for the limit to exist, it has to be a real finite number, meaning it can't be infinity or negative infinity. If the limit doesn't exist, it's either infinity or negative infinity or some sort of oscillating, alternating thing where you bounce back and forth forever and ever between two numbers. So let's look at this one. Does this limit exist? Well, let's take the limit as n goes to infinity of 5n plus 1 or 4n minus 2. You might all already be able to guess what the answer is going to be. I'm still going to show the work a couple more times. I'm going to divide everything by n to the first. I'm going to get 5n divided by n plus 1 divided by n over 4n divided by n minus 2 divided by n. And then all the things that are being divided by something that's getting really, really big are going to get really, really small. So I'm left with 5 over 4. Not the finite real number. So we would say, oh yeah, the sequence a sub n equal to 5n plus 1 over 4n minus 2 converges. And you could even say it converges to the value of 5/4. Although I will point out, you don't have to write any of that. Because if you've written this, the limit of that sequence is equal to 5/4, everybody agrees that we know that that means that the sequence converges to 5/4. So if you know that the limit as n goes to infinity is equal to something, you are also saying, and everyone is reading that as, oh, the sequence converges to that value. It's also fine to write. Well, let's look at this next one here, which I'm going to squeeze in down here. Let's say we have a sub n equal to -1 to the nth power. Fun fact, you can't really evaluate this in a meaningful way. If you try to do -1 to the nth power and you let n get really, really big, what's -1 to the infinity power? I don't know, is infinity even or odd? So here's what we should really do. We should actually inspect it and just look at some terms. If n equals 1, we're going to get -1 to the 1. If n equals 2, we're going to get -1 squared. If n equals 3, we're going to get -1 cubed, which is -1. It looks like this is just going to go back and forth forever and ever. I should stop writing these things. We're bouncing back and forth between -1 and 1 forever. We're not getting close to a single particular value, so the limit doesn't exist. So this limit does not exist, which means the sequence a sub n equal to -1 to the n diverges. But again, if you write that the sequence has a limit that doesn't exist, you are in essence already saying we know that the sequence diverges. Or if we had something like a sub n equal to, I don't know. Oh, did I do that here or there? I did there. So something like, I don't know, 5n squared plus 6 over 2n plus 3. Same sort of deal. Why don't you all take the limit of this one? Find the limit as n goes to infinity of this. And let me ask you real quick. Is everybody going to divide everything by n to the first or n to the second? N to the first. Good. Right on. So do it. Divide everything by n to the first and then take the limit and see what you get. All right. Let's show the work. We'll divide everything by n. I really think you can skip the step of writing each thing divided by n. Like you don't need to write 5n squared divided by n. You can do that simplification and just get 5n plus 6 over n over 2 plus 3 over n. Here's a wrong thing to write. You should not write that this is equal to the limit as n goes to infinity of 5n over 2. Even though we know that both these things are going to go to 0, you're not really supposed to see what some of the n's do, but not all of the n's at once. So if I'm saying that this 6 over n and this 3 over n are going to 0 because n is going to infinity, then I also should be saying that this n is going to infinity over here. So I can write this as 5 times infinity is infinity plus 0 over 2 plus 0, and infinity divided by 2 is infinity. One sec. Does this limit exist? Thumbs up for yes, thumbs up, thumbs down for no. We see some thumbs. Or in the middle if you're not sure. Does the limit exist? I'm not seeing a lot of thumbs. We see more thumbs, more thumbs, more thumbs, more thumbs. The limit does not exist. But we're being good students and saying, well, we know it doesn't exist. And also, I'm going to tell you that this sequence happens to get very, 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 very large as n gets larger and larger. How large? As large as you want. So here especially, even though the limit, we would say the limit is infinity, we're going to say that the sequence a sub n is divergent. It does not get close to any single number. You might say, James, it gets close to infinity. I'd be like, okay, what is that? Question, or did I answer your question? N squared? Yes, so the thing about going right away to infinity is you have to be careful of the sign. If that had been a negative 5n squared in front here, then the answer would have been negative infinity. So if the degree on top is larger than the degree on the bottom, we know that the answer is going to be either infinity or negative infinity, but we should still do the work to check. But I would say you're going to have an idea of what's going to happen. Just, I would still show the work, especially because on an exam, they're going to want you to show the work. Let's look at this next one. Some trig. Oh, question, sorry. Sure, so to be convergent, the sequence has to get close to some number. This sequence isn't getting close to. What number am I getting close to? Infinity is not a real number. So that's the problem here, is that infinity, right, is just an ideal. It's a direction, right? It's not actually a number. It's really, really big. How big? As far as you can go forever and ever and ever and ever and ever, right? There's no end. So you can't say it gets close to infinity because it doesn't. It just keeps getting bigger and bigger. This is just the thing we say, the notation we use to be like, hey, we know that this sequence diverges, doesn't get close to any number, but also we know it gets really, really positively big. So that's what's happening. Let's look at this next one. Ooh, cosine of n pi over 2. Let's just write out some terms. So n equals 1, I'm going to get cosine of pi over 2. N equals 2, I'm going to get cosine of 2 pi over 2, which is pi. N equals 3, I'm going to get cosine of 3 pi over 2. N equals 4, I'm going to get cosine of 4 pi over 2, which is 2 pi. And really, every time I'm just increasing by pi over 2. Right? The next one is going to be cosine of 5 pi over 2. Bless you. If you sneeze and I don't say bless you, I apologize. Bless you to everyone who sneezes. Gesundheit, whatever you want to say. And we can keep on going, right? If n equals 6, we get, okay, that's enough cosine of 6, whatever, or whatever. But what do these values actually equal to? So it is important that we have some idea of what cosine of pi over 2 or pi over 3 or pi over 6 or what those sine and cosine values of those common angles are. So these ones specifically, I like to kind of terribly call the 4 corners of the unit circle. Yes, I know a circle doesn't have any corners, but it's easier than saying the 4 like directions of the unit circle or whatever. So as you go around the unit circle, a full rotation through the unit circle is 360 degrees or 2 pi radians. So on the right side here, that's where we start at theta equal to 0 radians. And then if we go 90 degrees, that's going to be pi over 2 radians. And then 180 degrees is the same as pi radians. And then 270 degrees is the same as 3 pi over 2 radians. And a full revolution is 2 pi radians. And then if you go pi over 2 more, it's 5 pi over 2 radians. And pi over 2 more, it's 6 pi over 2 radians, and so on and so on and so on. So how do we find the trig values here? Well, on the unit circle, what do I mean when I say unit circle? What's special about a unit circle? What does unit mean? Well, in math, unit means 1. 1 is the unit. And so the unit circle is the circle whose radius is 1. That means if I go over here, I've gone 1 to the right, and that point is 1, 0. If I go up here, I've gone 1 up, that point is 0, 1. And I could zoom in a bit. Oh, really zoom in, okay. And then I could go 1 to the left, that's going to be -1, 0, and 1 down, that's going to be 0, -1. And then I hear some noise that is driving me crazy. If someone's listening to something, you could please turn it off. I would appreciate it. So my ears aren't always good, but sometimes they're good in a weird way. It's like, oh, there's something terrible. Anyway, so cosine. Why am I even drawing points on a circle? So yeah, we might as well say all the things. We'll come back to this in a second here. So just so everyone's aware of this, here's the bigger picture. Here's the idea. If you start at the positive x-axis and go an angle of theta, drop a perpendicular, call this distance x, this distance y, and the radius is still 1. Cosine of that angle is the adjacent side over the hypotenuse. And sine of that angle is the opposite over the hypotenuse. And that coordinate there is the coordinate over x up y. So what's important about the unit circle is that the points on the unit circle, the x coordinate and the y coordinate, are literally equal to the cosine of the angle and the sine of the angle. So cosine of your angle is equal to the x coordinate on the unit circle, and sine of your angle is equal to the y coordinate on the unit circle. So if we go back to the previous thing here, we can say, oh yeah, if I'm trying to find cosine of pi over 2, well, I'm going to go up to pi over 2, and the x coordinate is 0. The way I remember which one's which, by the way, is alphabetically. X comes before y, cosine starts with a C, sine starts with an S, cosine comes before sine. That's if you're ever worried about which one's first, alphabetical. X comes before y, cosine comes before sine. Cosine of pi is going to be -1. Cosine of 3 pi over 2 is going to be 0. Cosine of 2 pi is going to be +1. And then we're just going to keep repeating the same cycle of four things. 0, -1, 0, 1, 0, -1, 0, 1, forever and ever and ever until we die. And even beyond that. So, am I getting close to one particular value? No, I'm not. I keep doing the same thing forever and ever, bouncing back and forth between these three values. So this sequence, I should say, the limit of this sequence does not exist. So the sequence, oh my God, James. So the sequence diverges, holy smokes, say the right words. So a sub n equal to cosine of n pi over 2 diverges. It does not get close to any one particular value, but we wouldn't say it diverged to infinity because it isn't, right? It's not getting infinitely large. It's not getting negatively infinitely large. It's just diverging because it's not getting close to anything in particular. Cool. So, we zoom back out before I forget. There was something else I had. Let me make sure. One other thing I saw that was like, oh yeah, we should look at that. Two more things actually. So, a couple more sequences, and then we'll talk about some more recursive sequences. Oh, and also some path finding. Yeah. Sequences, I think sequences are kind of fun, but they're kind of annoying too. Oh my gosh, can I keep these papers in line? Maybe, maybe not. So let's look at something like this. A sub n equals, sure. I'm gonna make it more fun. 3 to the negative n plus 5 to the negative n. Whoops, you can't see that because I didn't zoom out enough and get reframed. Sorry about that. There we go. There's our sequence. So here's what I really want you to know about this. These are kind of like exponential functions. And there's something we should know about exponential functions because it's going to be useful for the rest of your calculus career. And that is, did I say the thing about your right hand and e to the x? Yeah, right. How if you look at your right hand, and I know mine is not the best for this, but there's like a line right there or more of a curve right there that looks like e to the x and a curve right there that looks like the natural log of x. So I would point out that if we graph e to the x, and yes, I'm going to use e to the x because it's kind of the standard. Here's what y equals e to the x looks like. And I want to point out that the limit as x goes to infinity of e to the x is, well, if we go way to the right, the function gets really big. On the other hand, really on the other side, the limit as x goes to negative infinity of e to the x is going to be, well, we're getting closer and closer to 0. And then if you reflect that graph across the y-axis, so if you graph y equals e to the negative x, by the way, that's the graph that's on your left hand. You can see, you can almost kind of see it on my hand here. It's like right there, kind of. Then the opposite limits are true. The limit as x goes to infinity of e to the negative x is equal to 0. And the limit as x goes to the left, the negative infinity of e to the negative x is infinity. Because the graph is going to be really big to the left and really close to 0 to the right. And it doesn't actually matter that my base is e. My base could have been 3 or 7 or 1,000, and these limits would still be true because exponential graphs have the same kind of shape as long as your base is larger than 1. So the reason I'm pointing that out is because I could really think of this as, if I'm trying to take the limit as n goes to infinity of 3 to the negative n plus 5 to the negative n, there are two good ways to think of this. One way is to say, well, 3 to the negative n is all like e to the negative x. And as I go to infinity, I'm going to get closer and closer to 0. That's actually not my preferred way of doing it, but it is the way that works. My preferred way of doing it is rewriting it. I would like to rewrite this so that my powers are positive. I'm going to write this as 1 over 3 to the n plus 1 over 5 to the n. And now to me, it's much more obvious that this limit's going to be 0 plus 0. Because I know that if n gets really, really big, 3 to a big number is a big number, right? 3 to the 5th power is 3 times 3 times 3 times 3 times 3. It's 243. That's already kind of big. 3 to the 1,000th power is almost incomprehensible, right? So this denominator is getting very large, which means the fraction is getting, somebody say it. Oh, yeah, very small. Both of them are getting very small. So this sequence is converging to 0 because the limit as n goes to infinity is 0. So we'd say that a sub n equals 3 to the negative n plus 5 to the negative n converges to 0. I don't know why I chose to write up number 0, but I did. Not for any good reason. Let's increase the level of difficulty just a tiny bit. Let's say I wanted to find instead, yeah, what do I want to do here? The limit, I want to start with the sequence, James. Sequence a sub n equal to, sure, 6 to the n over 3 to the n plus 5 times 6 to the n. Ooh, dangerous. Not really dangerous, just a little bit more work. So we actually have the same kind of idea here as we did for finding the limits where you have x to a power over x to a, or n to a power over n to a power, and we divided everything by n to the highest power. What we really should have been saying there is that we were dividing everything by the thing in the denominator that's getting biggest the fastest, right? When we divide everything by n cubed, it's because n cubed was the thing that was growing the biggest the fastest. Here, in the denominator, what's getting bigger faster? 3 to the n or 6 to the n? 6 to the n, I think relatively obviously, right? You can plug in a couple numbers, like you plug in 2, 3 squared is 9, 6 squared is 36. I mean, I think the choice is clear. Usually it's the larger base that's getting bigger faster, as long as you're going to positive infinity. So then if we try to take the limit here, as n goes to infinity of 6 to the n over 3 to the n plus 5 times 6 to the n, this pen looks like it's dying. Then we're going to divide everything by 6 to the n. So we're going to get 6 to the n divided by 6 to the n over 3 to the n divided by 6 to the n plus 5 times 6 to the n divided by 6 to the n. And now we're going to simplify. Limit as n goes to infinity. 6 to the n divided by 6 to the n is of course 1. 3 to the n divided by 6 to the n is 3 over 6 to the n, which I would reduce to 1/2 to the n. You don't have to reduce it, but I kind of want to. Plus 5 times 6 to the n divided by 6 to the n is just 5. Now, an important question. As n gets really large, what is 1/2 to the nth power going to do? Well, you're multiplying 1/2 times 1/2 times 1/2 times 1/2 a bunch of times. Is it getting bigger or getting smaller? Smaller. So ideally here, if you have a number that's larger than 1 raised to a really big power, it's going to get big. If you have a number between 0 and 1 raised to a big power, it's going to get smaller because you're making it smaller every time you multiply it by itself. So here you're going to get 1 over 0 plus 5, which is 1/5. So this sequence converges to 1/5. Cool. Okay, enough of sequences converging to things. I mean, not really, but you know, for now. Yeah, I covered the bases there. Let's talk about the other thing, which I kind of skipped over last class, but should have said more about, which was the finding the patterns. Sorry, I have my examples here somewhere. There we go. So sometimes we like to give you a just list of numbers, that's a sequence, and then ask you to tell me the formula for that sequence. And in my mind, there's like 3 types of things that come up. There's either, I'm just going to say them and then we'll give examples of each. There's things where you're just increasing by the same amount each time. Like you're adding 5 each time. There's things where you're multiplying by the same amount each time. So like you're multiplying by 2 each time. Or there's things where you're like, this is the kind of the hardest one. It's where it looks like something raised to a power. Let me give you some examples and then we'll talk about how they work. So here's a pretty straightforward example. We have that the sequence a sub n has the first 5 terms as, let's do that, 2, 5, 8, 11, and 14. So I would point out that's my a sub 1, that's my a sub 2, that's my a sub 3, that's my a sub 4, that's my a sub 5. How much are we increasing by every term? 3. So here's what I like to think about. When I write my a sub whatever is down here, a sub 1, 2, 3, 4, 5, my subscript, usually we think of it as n is increasing by 1 every time. Right, we're always just letting n bump up to the next integer. but I want my sequence to be increasing by 3 every time. So I know that if n increases by 1, I want to increase by 3, I'm going to multiply that n by 3 so that I can increase by 3 every time. So I know that my sequence should look something like a sub n equal to 3 times n plus something. Maybe not. Maybe it's just plus 0. So I'll notice now if I plug in 1, my a sub 1 is going to be 3 times 1, which is 3. But I want it to be 2. So how do I get from 3 to 2? What do? Subtract 1. And that's going to work for all of them, because then a sub 2 will be 3 times 2 minus 1, which is 6 minus 1, which is 5. And that's going to work for all of them, right? You can test anyone you want. A sub 5 is going to be 3 times 5 minus 1, which is 14. So that seems like a pretty good choice. It's not the only choice technically, but it is the only choice if you have to start at n equals 1. But I will just point out, so I'll say that my sequence is a sub n equal to 3n minus 1, with my first term being a sub 1 is the first term. The reason I mention this is because sometimes people like to start at 0 instead. So if we started at 0, you'd actually write it as a sub n equal to 3n plus 2, where a sub 0 is the first term. Because then if n equals 0, you get 3 times 0 plus 2, which is 2. And if n equals 1, you get 3 times 1 plus 2, which is 5, and so on and so on and so on. I wouldn't worry about that too much. I just felt like I should say it, but we don't really need to worry about it. Let's look at another example. Let's look at an example where we have some fractions. Let's say we have, no, I'm not going to be annoying. Let's say our sequence terms are 1/3, 4/7, 7/11, 10/14, 13, yeah, 13, and that is not a 14, that should be a 15, that should be a 15. Someone wrote a mistake there. I won't say who it is. Okay, so there are the first 5 terms of my sequence. Almost always, not always, but almost always, we kind of treat the denominator and the numerator completely separately. So I'm just going to look at the numerator first. Looking at the numerator, I see 1, 4, 7, 10, 13. Again, increasing by 3 every time, right? 1 plus 3 is 4, 4 plus 3 is 7, 7 plus 3 is 10, 10 plus 3 is 13. So I'm thinking, great, my numerator is going to be something like 3n. Then if I plug in 1 times 3 is 3, but I want to get 1, so I have to subtract off 2. Right? If I start at n equals 1, this is my a sub 1, a sub 2, a sub 3, and so on. So if I do a sub 1 for just the numerator, it's going to be 3 minus 2. If I do a sub 2 for just the numerator, it's going to be 3 times 2 minus 2, which is 6 minus 2, which is 4. Seems like we're good to go. Let's check out the denominator. Why don't you all check out the denominator? We've got 3, 7, 11, 15, 19. I think we're increasing by the same amount each time. So you should be able to figure out we have something times n plus or minus some number. I often will write something like this, like the difference is 4, the difference is 4. Oh, it's 4 every time. So then that's going to be a 4n, but if I plug in n equals 1, 4 times 1 is 4, but I want to get 3, so I'm going to subtract off 1. And then my sequence formula would be 3n minus 2 over 4n minus 1. Cool. Those are the easy ones. Then they get a little bit harder. Something like this. This has both of the harder things. All 3 of the harder things, actually. The third part's not that bad, though. So let's look at, do I have numbers? Sure, I can write numbers. No, I can't. No, I can't. So let's say we have the following. -1/4, positive, no, see, okay, I'm not going to make it extra hard. Positive 3/9, negative 27/16, and 27. What is going on here? Sorry, my 27. That is a mistake. Yeah, that's definitely a mistake. Sorry. I'm using my old notes here. I want negative 1/4, positive 3/9, negative 9/16, positive 27/25, and we'll go negative 81. What's the next number? 36. So I was saying to myself, kind of, that I was not going to make this extra hard by simplifying my fractions. It would be much, much harder to see the pattern here if I wrote 1/3 instead of 3/9, and if I reduced this to whatever it reduces to 27/12 or 9/4. 9/4. Yeah, sure, okay. But sometimes people will. And so sometimes you have to think about like what you need to do to this thing to make it so the pattern is more recognizable. Let's deal with the top part first. Let's actually deal with the negative part first. So we have an alternating sequence here. So that means we're going to need our a sub n to be a -1 to either the n or a -1 to the n plus 1. This depends on if we want to start with a negative or a positive. So since we're starting with a sub 1, we want a sub 1 to be -1. Well, -1 to the 1 is -1 versus -1 to the 1 plus 1 is -1 squared, which is positive 1. So we don't want the positive one because we want to start with a negative. So we don't want that. We want this. So that's what we're going to have out in front of everything. And then we're going to deal with the top and the bottom separately. Let's deal with the top. So the top, ignoring the alternating sign, I'm just going to write the positive terms. I have 1, 3, 9, 27, 81. And if I start trying to find the differences here, it's not helpful, although I often do look there. The difference between 1 and 3 is 2, 3 and 9 is 6, 9 and 27 is 18, 27 and 81 is 54. Yeah, 54. Well, that doesn't help. I might start looking at the differences again. The difference between 2 and 6 is 4, 6 and 18 is 12, 18 and 54 is 20. I should know what it is. It should be 36. Yeah. So here's the pattern I'm starting to see. There's not really a pattern so much as just an observation. No matter how many times I do this, it looks like the second term is always 3 times the first term. And the third term is always 3 times the second term. And the fourth term is always, right? It looks like every subsequent term is 3 times the previous term. So it looks like this is like maybe 3 to the 0th, and that's 3 to the first, and that's 3 to the second, and that's 3 to the third, and that's 3 to the fourth. If you see that you're multiplying by the same thing every time, right? This is a times 3, a times 3, a times 3, a times 3. That means you're going to have something like 3 to the n. Although it's not exactly 3 to the n. 3 to the n is not the right choice here. It's close, but it's not the right choice because if you plug in n equal to 1, what's 3 to the 1? 3. But I want to get 1. If I plug in n equal to 2, 3 squared is 9, but I want to get 3. So I need the power to be 1 less than it actually is. So I need to have 3 to the n minus 1. Then if I plug in n equals 1, I'll get 3 to the 0. If I plug in n equals 2, I'll get 3 to the first, and so on. Okay, the bottom part's probably the hardest part here. The bottom part really is just pattern recognition. Do those numbers look like they all have something in common? They have something in common. They're all squares. Another way to see this, though, if you didn't see that, is you can look at the differences of the differences. But we're not there yet. You can't really say that, James. I'll say this. So, and I'll say more about this later on when we start talking about derivatives. So if your numbers are 4, 9, 16, 25, and 36, if you look at the difference is 5, 7, 9, that's a 6, not a 3, 11. And the differences of the differences are 2, 2, 2. So if the differences are all the same, like in the previous examples we did, you just get something times n. But if the difference of the difference is always the same, then you get something like n squared. So here, we're going to have something like n squared, except by plugging in n equal to 1, I'm going to get 1 squared, which is 1, but I want to get 4, which is 2 squared. Right? That's 2 squared. That's 3 squared. That's 4 squared. So it looks like I have to take my n and first add 1 to it before I square it. But I don't want n squared. I want n plus 1 squared. So here, my final result would be that my a sub n is equal to -1 to the n times the fraction 3 to the n minus 1 divided by n plus 1 squared. It's a little bit gross, but it works. So those are the 3 kind of things I look for. Is it increasing by the same amount each time? Great. It's something times n. Is it multiplying by the same amount each time? Oh, great. It's that multiplication thing to the nth power. Or does it look like there's a bunch of square numbers or cubic numbers? Or those are really the only ones you'll see. Those are kind of the things we look for. Okay. 247. Oh, let's keep the water in your mouth, James. Yeah, okay. All right, let's circle back around to these recursive sequences, also known as difference equations. Oh, yeah. Oh, yeah. Sorry, I'm kind of going back and forth with you. No, we'll talk about that in a minute. Okay, so recursive sequences again. AKA difference equations. All right. So we did one example last time, but let's look at a more interesting example. So let's say we have the following recursive sequence. A sub n plus 1 is equal to the square root of 2 times a sub n, and we are given that the first term is a sub 1 equal to 3. So the question we really want to ask is twofold. What are the fixed points? And there might be more than one. And which of the fixed points, if any, seem like a candidate for the limit, or a possible limit? This question does require the use of a calculator a little bit to kind of see what's going on. So before we answer either of those questions, let's just start plugging in some values. So if I plug in 3, then a sub 1 plus 1 is equal to the square root of 2 times a sub 1, which is the square root of 2 times 3, which is the square root of 6, which is approximately 2.45. So notably, we plugged in a sub 1 equal to 3. We got a sub 2, which was a little bit less. Okay, good to know. Let's do a couple more. A sub 3 is going to be the square root of 2 times a sub 2, which is the square root of 2 times the square root of 6. And then these get a little bit dicey. That's about 2.21. So even smaller. Let's do one more. A sub 4 is the square root of 2 times a sub 3, which is the square root of 2 times the square root of 2 times the square root of 6, which is kind of gross. Just get the gross for every time. That's about 2.10. And a sub 5 is going to be the square root of 2 times all of that, which is the square root of 2 times the square root of 2 times the square root of 6, which is approximately 2.05. If we had to guess right now, I think a reasonable guess would be that the limit's going to be what? Yeah, it seems like it's going to be 2. Now, here's something I would do just to kind of point out. If you plugged in 2 exactly, so if you plugged in 2, what's 2 times 2? What's the square root of 4? If you plug in 2 exactly, you get 2 back. And if you plug in the number a little bit bigger than 2, 2 times the number bigger than 2 is a little bit bigger than 4. And the square root of a number a little bit bigger than 4 is a little bit bigger than 2. So every time you plug in a number a tiny bit bigger than 2, you're going to get back a number that's still a tiny bit bigger than 2. So what we're doing here, starting with a number bigger than 2, is we're never going to be able to get to a place where we're less than 2. So that's good to think about. All right, let's find the fixed points, or the equilibrium points. So the fixed points, and again, all we're doing is we're asking the question, what numbers can I find so that if I plug that number in, I get the same number back? So what value for a sub n will give me the same a sub n plus 1 value? So the way I do that is I literally replace a sub n plus 1 and a sub n with the same variable. We usually use capital L because we're thinking of it as being a limit. So I'm going to write capital L equals the square root of 2 times capital L. That's just the process, right? Just as someone says, find the fixed points or find the equilibria, just replace every a sub whatever, a sub n plus 1, a sub n plus 2, whatever a sub n's you have, replace all of them with capital L or whatever letter you happen to like better than L. Then we solve this. I'm going to square both sides. So L squared equals 2L. I'm going to bring everything to the same side. L squared minus 2L is equal to 0. I'm going to factor because that's the safe way to do it. So L times L minus 2 equals 0. So I either get L equal to 0 or L equal to 2. And in this case, it certainly seems like 2 is the right choice for the limit. So L equal to 2 seems like the limit based on our work we did over here. Kind of interestingly, if you started with a number less than 2, like 1, and plugged it in, the limit would still be 2. Because you think about this, if you plugged in 1, you would get the square root of 2 times 1, which is the square root of 2. And the square root of 2 is about 1.4. So you plugged in 1 and you got back something that was smaller or bigger. Bigger. And if you plug in that number, square root of 2, you get the square root of 2 times the square root of 2, which is going to give you back something even bigger. And it's just going to keep getting bigger and bigger and bigger, closer and closer and closer to positive 2. So whether you start on the bigger side of 2 or the smaller side of 2, as long as it's positive, then you're going to get closer and closer to 2. Kind of interesting. Some language we're eventually going to use, even though we're not there yet, is that we would say that 2 is a stable equilibrium here. Because even if you move a little bit away from it, you kind of get pushed back towards it. Whereas 0 is an unstable equilibrium. If you plug in 0, you're going to get 0 back, right? 2 times 0 is 0, square root of 0 is 0. But if you move even just a little bit bigger than 0, like if you plugged in 0.01 and did this process a few times, you would get larger and larger and larger. Yeah, you would. Kind of neat. All right, let's look at a couple more examples. I like this one, yeah. So let's say we have a sub n plus 1 equal to 12 over 1 plus a sub n. And our first term is a sub 1 equal to positive 1. The bummer about some of these recursive sequences especially is you kind of have to use a calculator to start evaluating them. If you're asked to find the terms, because it's just like, if I plug in 1, okay, 1's fine. So a sub 2 is going to be 12 over 1 plus my a sub 1, which is 1. And 12 over 2 is 6. Okay, good. Good so far. And then my a sub 3 is going to be 12 over 1 plus my a sub 2. It's going to be 12 over 7. Not loving that. That's about 1.71. And then my a sub 4, if I plug in that, I'm going to get 12 over 1 plus 12 over 7, yeesh, which is approximately 4.42. So it kind of feels like I'm bouncing back and forth, right? I'm small at 1, I'm big at 6, I go back down to 1.71, and go back up to 4.42. And then the next one's going to be something like 2 point something. Yeah, it's about 2.21. So a sub 5 is approximately 2.21. So it seems like we're kind of bouncing back and forth around what our limit might be. So let's find the fixed points. In fact, I want you all to find the fixed points. So solve L equal to 12 over 1 plus L. And I would say your first step would be to multiply both sides by 1 plus L. Multiply at the left side, bring everything to the left, factor, and see what your possible fixed points are. All right, so here's what should happen. Multiply both sides of 1 plus L. We got L times 1 plus L on the left. We got 12 on the right. Distribute the L. You get L times 1 plus L times L, which is L plus L squared, still equal to 12. Bring everything to the left and rewrite it in the typical way, meaning the highest powers of L first. So you got L squared plus L to the first minus 12 equals 0. Then we're going to factor. We're looking for numbers that multiply to negative 12 and add up to positive 1. Those numbers are positive 4 and negative 3. Find the solution, set each rate equal to 0. L plus 4 equal to 0 is going to give us L equal to negative 4. And L minus 3 equal to 0 is going to give us L equal to positive 3. And based on the numbers we saw previously, which of those numbers seems like it might be a reasonable guess for the limit? Negative 4 or positive 3? Gotta be positive 3, right? Could you even get a negative number if you start with a negative number? Sorry, with a positive number? No, right? Because if you plug in a positive number, 1 plus a positive number is still positive, and 12 divided by a positive number is still positive. You'll spit back out a positive number. And then you'll plug that back in, and it'll still be positive. So here, if you start positive, you're going to always end up being positive. I think even if you start negative, you'll still end up being positive eventually. So definitely not the negative 4. That is not a good candidate. But L equals 3 is probably the limit of this sequence. Look at 1 or 2 more, and then we'll move on to something else. We still got a good 30 minutes. So let's look at this sequence here. Yeah, this one's kind of fun. So let's look at A sub n plus 1 equal to 4 over A sub n. And we'll start with A sub 1 equal to 1. And I'm going to actually do the opposite thing first this time. Let's find the fixed points first. So here are my fixed points. Are going to be, well, I'm going to say L equals 4 divided by L. Multiply both sides by L. You get L squared equal to 4. And then take the square root, you get L equal to plus or minus the square root of 4. Plus or minus 2. You can always check this to see if it makes sense. Like if I plug in 2, 4 divided by 2 gives me back 2. If I plug in negative 2, 4 divided by negative 2 gives me back negative 2. So that's what it means to be a fixed point. If you input that value, you get back. Nobody wants to say anything? You get back the same value? Yes, thank you. I know you all are thinking it, just don't want to say it. It's okay. So let's start plugging in our numbers and see what happens. You plug in 1, A sub 2 is going to be 4 over A sub 1, which is 4 over 1, which is 4. Okay. You plug in the next one, A sub 3 is going to be 4 over A sub 2, which is 4 over 4, which is 1. But I know that if I plug in 1, I'm going to get 4. If I plug in 4, I'm going to get 1. So the next term, A sub 4, is just going to be 4 over 1, which is 4. And the next term, A sub 5, is going to be 4 over 4, which is 1. And I keep going back and forth from 1 to 4 to 1 to 4 to 1 to 4 forever and ever and ever. This recursive sequence doesn't converge. How annoying. At least if you start at 1. What if we started somewhere else? What if we started at, say, I don't know. I don't need to write the same thing. I guess I could write it again. What if we started at A sub 1 equal to 3? Well, then A sub 2 is going to be 4 divided by 3. Okay, looking all right so far. We're getting, seems like we're getting maybe closer to 2. And then A sub 3 is going to be 4 divided by 4/3. When you divide by a fraction, you flip and multiply. You get 4 times 3/4, which is 3. Oh no, we're back where we started. So this is an example of a recursive sequence that actually never converges unless you happen to start at the equilibrium. No matter where you start, unless it's at 2 or negative 2, you're always going to get this back and forth thing where you plug in a number, you get something else, and then you plug in something else, and you get back where you started. It always bounces back and forth between 4 over that number and 4 over 4 over that number. Do you know what 4 over 4 over a number is? Just the number. Yeah, kind of funky that you keep coming back and forth like that, but it does. And then might as well, since we're here, could you find a pattern for this sequence? 1, 4, 1, 4, 1, 4 forever and ever and ever. Ooh. Oof. It's very doable. Here's how you do it. You split the difference. So from 1 to 4, the difference is 3. Half of that is 3 halves. So you're going to go to halfway between 1 and 4. So the average of 1 and 4, if you like. 1 plus 4 divided by 2 is 5 over 2. And then you just want to keep adding 3 halves or subtracting 3 halves. So we're going to do plus 3 halves times negative 1 to the n. If n equals 1, I get 5 halves minus 3 halves, which is 2 halves, which is 1. If n equals 2, I get 5 halves plus 3 halves, which is 8 halves, which is 4. And it goes back and forth and back and forth and back and forth and back and forth. So there's always a way to write a sequence for something that goes back and forth between 2 numbers. You just find the middle ground, and then you add or subtract how far it is from the middle to either end. All right, that's probably enough. Oh, he said hopefully before you look at this last example. So I should ask you all, have you been talking about geometric series in class? I don't see any yes. Is that correct? I mean, not good. They are interesting and useful. But if we're not covering them yet, I should probably not cover them yet. Let's go ahead and, well, let me ask, have you started talking about limits yet? Okay, so I mean, we obviously already have talked about limits in the limits of sequences, but now moving on to the limits of functions. And where x is, ooh, oh, weird. Sorry, my next is like, where x is approaching something that's not infinity. Like the limit as x approaches 2 of some function. That sound? Yes, okay, all right. So that's where I feel like I saw someone about to like ask a question though. No? Oh yeah. Good question. Let's do another one. Let's make it slightly easier. Let's say our sequence is something like 7, 13, 7, 13, 7, 13, forever and ever and ever. If I wanted to find the formula for this, and again, this is my n equals 1, my n equals 2. I'm going to actually do it kind of backwards from the way I did it before. So I know that whenever I have something that bounces back and forth between 2 numbers, I really just need to take a negative 1 to the n and modify it so that it gives me what I want. So I know that negative 1 to the n gives me negative 1, 1, negative 1, 1, negative 1, 1. Okay, but I don't want to go, so really I'm going from 0 down 1, from 0 up 1, from 0 down 1, from 0 up 1. But I don't want to go down 1 and up 1. I want to go down 3 and up 3. Because the middle of 7 and 13 is what? 10. Or the average of 7 and 13 is what? 10. So I know from 10, I want to subtract 3 to get 7 and add 3 to get 13. So I'm going to say I want 3 times negative 1 to the n. And then I'm going to get 3 times negative 1, 3 times positive 1, 3 times negative 1, 3 times positive 1. And then what do I have to add to all those numbers to get the actual numbers I want? 10. So I'm going to say 10 plus 3 times negative 1 to the n is going to give me 7, 13, 7, 13, 7, 13, forever and ever and ever. Or alternatively, you could say, I want the average. And then I know I need 10 minus 3, 10 plus 3, 10 minus 3, 10 plus 3, which I'm going to write as 10 plus 3 times negative 1 to the n. Be careful. This is not at all the same as 10 plus negative 3 to the n. Although they are both divergent, negative 3 to the n gets to be really giantly negatively big and positively big. Right? If n is 1,000, you have negative 3 to the 1,000th power, which is a huge number. Whereas here, if n is 1,000, you have 3 times 1, which is 3. So just be careful you don't make a mistake there. All right. Yeah, let's spend the last 20-ish minutes here talking about limits. That probably doesn't come up very often, but it does occasionally come up that you have like this oscillating thing, like just back and forth. I'm like, oh, well, there's an easy way to do it. It's harder if there's three different numbers. Like if it's 1, 0, -1, 0, 1, like that's challenging. So let's graph the following piecewise function. F of x equal to, I prefer that choice, yeah. X squared plus 1 when x is less than 0. X plus 1 when x is between 0 and less than or equal to 2. And, all right, let me think for a second here. Yeah. 6, yeah, 6 minus x squared when x is bigger than 2. So we're just going to graph this. Try and do a decentish job here. Decent-ish. So starting with the topmost piece or the leftmost piece, x squared plus 1 is just your usual parabola shifted up by 1. Everywhere left of 0. So I'm going to say, well, it looks like your usual parabola. If I could plug in 0, I would get 0 plus 1. But I can't yet, so I'm going to have an open circle there. And then my parabola just looks like this. Usual parabola shape. Doesn't have to be perfect. Okay. And then you could, I guess I could plot another point. If I plug in -1, that's the point. -1, 2. I don't really need that point, but there it is. But now, in this middle piece, if I set x equal to 0, I get 0 plus 1, which is 1. So that middle piece actually does fill in that open point perfectly. And then I know it's a straight line. It's y equals x plus 1. It's got a slope of +1. It's got a y-intercept of 1. So I'm going to go over 1, up 1, over 1, up 1. Or really what I would do is I plug in 2. 2 plus 1 is 3. So I know when I plug in 2, I should get a y value of 3. And there it is. And there's a straight line between those 2 points. They're both filled in circles because x is defined to be equal to 0 and equal to 2 for this function. Finally, the graph of 6 minus x squared looks like your usual parabola function flipped down and then shifted up. So if there was a y-intercept, it would have been +6. And then my graph would have kind of gone down like that. And then starting right here, when x would have been 2, 6 minus 2 squared is 6 minus 4, which is 2. So I'm actually down here. I didn't draw it steep enough. Okay, though. My parabola would have looked like that, and then actually started right there. Labeling my points, that's the point 2, 3. This would have been the point 2, 2. All right, there's my nice piecewise looking graph. Talk about some limits. So here's the question that we're going to start with. As x gets really close, I'm just going to write close, but I'm going to say really close to 0 from the left side, what does f of x get close to? I should say, what value does f of x get close to? Well, that is a lot of words to write something. I don't want to write that many words. So here's the mathematical notation for all of that. What is the limit as x approaches 0 from the left-hand side of this function f of x? That's what all of this says. The limit as x approaches 0 of f of x is just asking what y value is the function getting closer and closer to as x happens to get closer and closer to 0 from the left side. That's a little minus. The minus sign means from the left side. The plus sign means from the right side. So if x approaches 0 from the left-hand side, the y values are getting closer and closer to what y value? It looks like 1, and it is 1. So we say the limit's 1. On the other hand, or the other side, what about as x approaches 0 from the right-hand side? Well, if I take the limit as x approaches 0 from the right-hand side of f of x, it's good to look at the graph. If I approach 0 from the right, the y values are also getting closer and closer to a value of 1. So it's going to be 1 as well. And here, since the left-hand limit and the right-hand limit happen to have the same value, we say that the double-sided limit, or the overall limit, is also that value. So both of these things together tell us that the limit as x approaches 0 from both sides of f of x is also 1. And this is generally a true statement. For the limit to exist, the left-hand side limit and the right-hand side limit have to both exist and be equal to each other. We'll write that down in the next page in a second. Let's look at what's going on at x equal to 2. So if I look at the limit as x approaches 2 from the left-hand side of f of x, let's see. Sorry, I kind of wrote on this already. I can use green here. So if we're approaching 2 like that, then the y values are approaching, they're getting closer and closer to a y value of what? Yeah, 3. On the other side of 2, as x approaches 2 from the right-hand side of f of x, we can see that as the x values approach 2 from the right, the y values are approaching also 2. All right, we're getting closer and closer and closer to a y value of 2. Now, I'll point out, and this is a really important piece of information here, we never actually get to a y value of 2. You can plug in if you plugged in x equal to 2.0001, then the y value, or f of 2.0001, if you want, would be 6 minus 2.0001 squared, which I guess I could actually get out of the calculator to see what it actually is. If we do that, we're going to get 6 minus 2.0001 squared, which is really close to 2. Can you see that? 1.9995, approximately. So the point is about closeness. If x is getting really, really close to 2 from the right, the y value is getting really, really close to 2, period. Now, if you were to ask about the overall limit here, since the left-hand limit and the right-hand limit don't match up, we say that the overall limit does not exist. So the double-sided limit, or the overall limit as x approaches 2 of f of x, does not exist. When you're writing this, when you get limits that don't exist, do me a small favor, just because I hate it. Don't write equals does not exist. Just write the limit does not exist. You don't need an equal sign there because you can't really equal something that doesn't exist. If you do it, it's fine. It's not a crime. I just think it's terrible. So, I'll hold you in high regard if you don't write equals does not exist. I know my opinion is very important. It's not really. So, there was something. Oh, so here's what I want to say. So, we would say that the limit as x approaches a of f of x exists if and only if the limit as x approaches a from the left of f of x equals the limit as x approaches a from the right of f of x. And for them to be equal, they both have to exist. If both those limits exist and they equal each other, then that limit exists and is equal to the same thing. So this notion of closeness is super duper important. Also, let's do this one. Something else that's really important about a limit is the limit doesn't care what's happening exactly at the point we're approaching. It cares what happens really, really, really close to it, but not actually at it. Here's what I mean by that. Let's look at the following piecewise function. We're going to graph f of x equal to the piecewise function x plus 2 when x is less than 1, 7 when x is equal to 1, and 4 minus x squared when x is bigger than 1. So it's a straight line when x is left of 1. it's x plus 2. So the y-intercept is 2. And if x could be 1, 1 plus 2 would be 3. It's going to look like that to the left. Straight line. If x is 1, I made that number too large. Oh well. 3, 4, 5, 6, 7. If x is equal to 1, the y value is exactly 7. And if x is bigger than 1, then it looks like the downward opening parabola, 4 minus x squared. And again, if you plug in 1 there, even though we technically can't, 4 minus 1 is 3. So you would get the parabola that does this. It's going to go like that. And then we're going to start it right here. Going to hit 2. And look like that. So there's my graph. Notably missing that point right there. I have that point there instead. The whole there is 1, 3. So then we can ask the questions. What's happening as x approaches 1 from the left-hand side? Well, the limit as x approaches 1 from the left-hand side of this function, if you look at the function, it's getting closer and closer to 3. In fact, you could pick numbers just a tiny bit smaller than 1, like 0.999. If you plug them into the function, 0.999 plus 2 is 2.999, which is pretty close to 3. On the other side of things, as x approaches 1 from the right of f of x, in fact, I could be, so you know what I could be doing here is I could be showing a little bit more work. Instead of just looking at the graph, I also could have said, here's an alternate path, by the way. I could have said that this is equal to the limit as x approaches 1 from the left of the piece of the function where x is less than 1, which is the piece where the function is equal to x plus 2. And I can say, oh, well, x is getting close to 1, so x plus 2 is getting close to 1 plus 2, which is 3. I can do the same thing here. If x is bigger than 1, I'm using the piece of the function where x is bigger than 1. So I can say that this is equal to the limit as x approaches 1 from the right of 4 minus x squared. X is getting really close to 1. 1 squared is getting really close to 1. Or x squared is getting really close to 1. And 4 minus that's getting really close to 4 minus 1, which is 3. So the limit from the right is 3, the limit from the left is 3, and by the thing we said up here, that means the overall limit exists and is also equal to 3. So it is, in fact, true that the limit as x approaches 1 of f of x, the double-sided limit, is equal to 3. Even though f of 1 is not 3. F of 1 is 7. The limit doesn't care. The limit isn't about what's happening at x equals 1. The limit is all about what's happening around x equals 1, but not at x equals 1. It's a really important facet of how limits work. Do I have it anymore? Yeah. I'll probably say it like 100 times. It's really important. So graphically, that's the idea with limits, is you're just asking what's the y value getting closer to as the x value is getting closer to whatever we said it's getting closer to. But we don't always want to draw the graph. We don't almost ever want to draw the graph. So how do we do this in practice? Well, let's look at an example. Let's say we want to find the limit as x approaches 3 of 2x squared minus 5x plus 1. I don't know exactly what that graph looks like, but I know it's a parabola, and I know it's continuous. I know we haven't defined continuity yet, but we're going to soon. But you probably have an idea from a very kind of generic point of view is that a function is continuous when you can draw it without lifting your pencil off the paper or your chalk off the chalkboard. So this parabola, I don't know exactly what it looks like, but it's something like this. Probably. I don't actually care. But the point is that no time did I have to lift my pen off the paper to draw. Unlike the previous graph, where I definitely had to lift my pen off the paper to jump up to there and then jump back down to there. So notably, at 3, whatever you're doing from the left or from the right should get closer and closer to what the function value actually is. So there's this idea that's called essentially the evaluation theorem, which is that if your function is quote unquote normal, you usually just plug in whatever x is approaching and get the limit value. So here, if you just plug in 3, you get 2 times 3 squared minus 5 times 3 plus 1, which is 2 times 9 minus 15 plus 1, which is 3 plus 1, which is 4. And that's correct. And for almost any function, as long as it's defined at the point you're looking at, you can plug in that point and get a value out. True for, so I should say, this works for lots of functions. It works for polynomials, they're the best. It works for rational functions, which are polynomials divided by polynomials. It works for any trig function as long as it's defined there. So you can't plug in a value that would give you a vertical asymptote for tangent or cosangent, but you can certainly plug in any other value and it totally works. It works for exponential functions like e to the x or 2 to the x. It works for logarithmic functions as long as you're not plugging in a negative number or zero. So really, any function that is continuous on its domain, this idea works where you can just plug in the value. And I know, again, we haven't really defined continuity, but we'll get there eventually. The short answer is the first thing you should do when you're confronted with a limit is try plugging in the value that x is approaching and see what happens. If you get a real number, unless you have a piecewise function, that's probably the answer. I will point out it wouldn't have worked here, right? If I said what the limit as x approaches 1 and you plugged in 1, what would you get? What number do you get for this function if you plug in 1? It's a lucky number sometimes. It is 7, right? If you plug in 1, you get 7. Is that what the limit was? No, it was not. Right? The limit was 3. So piecewise functions are usually used primarily as examples of functions that have limits that are not equal to their function values. But other than kind of funky piecewise functions, most regular-ish, normal-ish things work the nice way, where you plug it in and you get the nice answer. So for example, if I wanted to find the limit as x approaches 8 of the cube root of x plus e to the x minus, I don't know, 8 plus 5, I'm just going to plug it in and get cube root of 8 plus e to the 8 minus 8 plus 5, which is 2 plus e to the 0 plus 1, sorry, plus 5, which is 2 plus 1 plus 5, which is coincidentally and very much not on purposely equal to 8. I did not mean for it to also be equal to 8. That's just a coincidence. It could have just as easily been 7 if I added 4 at the end. Sorry for that coincidence. I do not like that. That's the same, but oh well, something happens. All right. So, as you might have guessed, that's not what's usually going to happen. How much time do I have? I have enough time. Cool. Let's say I want to find the limit as x approaches 3 of x squared plus 4x minus 21 over x minus 3. You should still start a problem like this by plugging in what x is approaching and seeing what happens. So I plug it in, I get 3 squared plus 4 times 3 minus 21 over 3 minus 3. I get 0 on the bottom, which is already a problem. And I also get 0 in the numerator. 9 plus 12 is 21, minus 21 is 0. So 0 over 0 is very special. Very much like infinity divided by infinity. It's an indeterminate form. It can literally take on any value. And when you see 0 over 0, what you should think is that's an indeterminate form. No, what you should really think is I have to do more work. So 0 over 0, really what that means for all of us is do more work. 0 over 0 is never a final answer. It's I need to do something else so I get a final answer that's actually a nice real number. Occasionally it'll end up being still some sort of undefined thing, but at this stage we don't know that yet. So typically the work is going to be do some algebra. Like in this case, I can factor, do some canceling. So I'm going to rewrite this as the limit as x approaches 3 of x minus 3 on the bottom. And the numerator, well, here's something worth knowing as well. This is actually called the fundamental theorem of algebra. If I plug in a number to a polynomial and it ends up equaling 0, it means that x minus that number had to have been a factor. So since I plugged in 3 to the top part and got 0, I know that x minus 3 has to be a factor. And then the other factor I can figure out pretty easily, because I know I need x times x to give me x squared. I need negative 3 times positive 7 to give me negative 21. It's a really useful piece of information, actually. Okay, here is the crux of why this all works. I'm going to take the limit as x approaches 3, meaning I'm going to get really, really, really close to 3, but not equal to 3. So let's say I plugged in like 3.00001. If I plug in x equal to 3.0001, what's going to happen here? I'm going to get 3.0001 minus 3, good God, James, 3.001 minus 3 times 3.0001 plus 7. I should have used less zeros, divided by 3.0001 minus 3. And now here's an important question. Everyone can show me the answer on their fingers. What's 3.0001 minus 3 divided by 3.0001 minus 3? Fingers. Yeah, that many. Exactly. It's 1. And as long as you're not picking 3, that's always going to cancel to 1. And you know what? We're never picking 3 because we're getting really, really close to 3, but not equal to 3. That's why this idea of the limits is really important. It allows us to factor and cancel this and not have any consequences. We're just saying, oh yeah, look, as long as x isn't 3, which is what this limit really means for us, it's totally fine to cancel those because they're always going to divide by each other and give us 1. So this is the same as the limit as x approaches 3 of just x plus 7. Because as far as these two functions are concerned, they're the same everywhere but 3, and the limit doesn't care what's happening at 3. And then we can just say, oh, well, x plus 7, I can just plug in 3 for x and get 3 plus 7, which is 10. Graphically, here's what's going on. If you graph this function, well, it looks like the line y equals x plus 7, except we're missing a point when x equals 3. So it looks kind of like this. At 3, you've got a hole right there. So when x is 3, y would have been 10. So you can see that, oh yeah, as we approach 3 from the left, the y values get really close to 10. As you approach 3 from the right, the y values get really close to 10. But if you actually plug in 3, it's completely undefined. But again, the limit doesn't care what happens at 3. It cares what happens near 3. So this limit would be equal to 10. And then I'll just say in the last seconds I have here is that until you are, so I've written the limit every time as long as there's a variable there. So I have the limit as x approaches 3 of some things with x's equals the limit as x approaches 3 of something with x's. And then as soon as I plug in a number for x, I no longer write the limits. So x's need the limit, no x's, no limit. See you all next Tuesday.